Strong acid, strong base titrations. The reaction between the strong acid HCl and the strong base NaOH can be represented by NaOH aqueous plus HCl aqueous to give NaCl aqueous plus H2O liquid, or by the net ionic equation OH minus aqueous plus H plus aqueous to give H2O liquid. The titration curve shown here is a plot of pH against volume of NaOH. It shows changes that occur when 25.0 ml of 0.100 molar of HCl is titrated against 0.100 molar of NaOH. At the start, the pH of 1 is low. As titration progresses, the pH increases slowly. When the volume of NaOH solution added is close to 25.0 ml, the reaction mixture nears equivalence point, which is the point when complete neutralization between stoichiometric quantities of acid and base occurs. The pH starts to climb rapidly. Adding just a little drop of NaOH solution so that exactly 25.0 ml has been added causes a sharp or steep rise in pH from around 4 to 10 as equivalence point is reached. Equivalence point occurs when pH is equal to 7. When more drops of NaOH solution are added after the 25.0 ml mark, the pH increases slowly. Weak acid, strong base titrations. The reaction between a weak acid and a strong base can be represented by the reaction between ethanoic acid and sodium hydroxide to give sodium ethanoate salt and water. The titration curve shown here is a plot of pH against volume of NaOH solution. It shows changes that occur when 25.0 ml of 0.100 molar of ethanoic acid is titrated against 0.100 molar of NaOH. At the start, the pH of 3 is somewhat low. As titration progresses, the pH slowly increases. When the volume of NaOH solution added is close to 25.0 ml, the reaction mixture nears equivalence point, which is the point when neutralization occurs. The pH now starts to climb rapidly. Adding just a little drop of the NaOH solution so that exactly 25.0 ml has been added causes a sharp rise in pH from around 7 to 10 as equivalence point is reached. Equivalence point occurs when pH is equal to 8.5, that is greater than 7. Beyond the 25.0 ml mark, the pH slowly increases as more NaOH solution is added. Why is the equivalence point at 8.5 and not 7? At equivalence, another reaction occurs. It is the ionization of ethanoate in water. This reaction is also called the hydrolysis of salt. Ethanoate is formed from the earlier neutralization reaction. Ethanoate is a base as it can accept H plus from water to form ethanoic acid. Water is an acid as it can donate H plus to ethanoate. When it does so, it becomes the hydroxide ion. The sodium cation doesn't change and remains the same as before, so it is known as a spectator ion. When the hydroxide ion is generated, the hydroxide ion concentration increases. This is the cause for the pH at equivalence point being higher than 7. Strong acid, weak base titrations. An example of a strong acid, weak base reaction is that between the strong acid aqueous HCl and the weak base aqueous NH3 to give aqueous ammonium cation and aqueous chloride anion. The titration curve shown here is a plot of pH against volume of HCl solution. It shows changes that occur when 25.0 ml of 0.100 molar of aqueous ammonia is titrated against 0.100 molar of HCl. pH of around 11.3 at the start is somewhat high. As titration progresses, the pH decreases slowly. When the volume of HCl solution added is close to 25.0 ml, the reaction mixture nears equivalence point, which is the point when neutralization occurs. The pH starts to fall rapidly or steeply. Adding just a little drop of HCl solution so that exactly 25.0 ml has been added causes a sharp drop in pH from around 7 to 3 as equivalence point is reached. Equivalence point occurs when pH is equal to 5.5, that is, less than 7. Beyond the 25.0 ml mark, the pH slowly decreases as more HCl solution is added. Why is the equivalence point at 5.5 and not 7? At equivalence, another reaction occurs. It is the ionization of the ammonium cation in water. It is also called the hydrolysis of salt. Ammonium cation is formed from the earlier neutralization reaction. Ammonium cation is an acid, so it donates H plus to water to become ammonia. Water is a base, so it accepts H plus to become the hydronium ion. When hydronium ion is generated, there is an increase in the hydronium ion concentration in solution. This is the cause for the pH at equivalence point being lower than 7. The chloride anion doesn't change and remains the same as before. Recall that chloride is the weak conjugate base of the strong acid HCl. It has essentially no ability to accept H plus from water. It is also a stable ion due to its negative charge being well dispersed over its surface area. We can think of it as a spectator ion. You are not required to know the titration curve associated with the neutralization reaction between a weak base and a weak acid. Indicators are used in titration to indicate the end point of a reaction. An indicator is usually a weak organic acid or base that has distinctly different colors in its unionized and ionized forms. We may represent an indicator as HIN. In aqueous solution, HIN ionizes and becomes H plus and its conjugate base IN minus. According to Le Chatelier's principle, when acid is added to an aqueous solution of the indicator at equilibrium, the system feels disturbed by the high concentration of H plus ions. To counteract the increase in H plus concentration, the system tries to decrease it by shifting the equilibrium position to the left, thus favoring the formation of the unionized indicator HIN. So in acidic medium, the ionization of HIN is suppressed. When hydroxide ions are added to an aqueous solution of the indicator at equilibrium, the hydroxide ions readily neutralize the H plus ions in solution. According to Le Chatelier's principle, the system feels disturbed by the sudden drop in H plus ion concentration. To counteract the loss of H plus ions, the system tries to add back the H plus ions by recreating them. It does this by shifting the equilibrium position to the right, that is, by getting the unionized indicator, HIN, to ionize to generate H plus and IN minus. Thus, in basic medium, the conjugate base IN minus is favored and predominates. For example, phenolphthalein indicator is colorless in acidic or neutral solution and pink in basic solution. The end point in a titration can be seen with the use of an acid-base indicator. The end point of a titration is the point at which the color of the indicator changes. It is not the same as the equivalence point. it is only an estimate of the equivalent point. Not all indicators change color at the same pH, however, so the choice of indicator for a particular titration depends on the strength of the acid and the base used in the titration. To find the endpoint of a titration, we must select an appropriate indicator. There aren't indicators that change color at a single pH which perfectly matches the equivalent point of a titration. Rather, indicators change color over a pH range. In practice, we select an indicator whose color change occurs over a pH range that coincides with the steepest part of the titration curve. There are two titration curves shown here. The red curve represents a weak acid, strong base titration, while the blue curve represents a strong acid, strong base titration. The indicator phenolphthalein can be used to determine the endpoint of either titration since its change in color coincides with the steepest part of each curve. Methyl red indicator can only be used for the blue curve, that is, the strong acid, strong base titration, but cannot be used for the red curve, that is, the weak acid, strong base titration, because its color change does not coincide with the steepest part of the curve. Here are examples. Which indicator listed in Table 17.3 would you use for the acid-base titrations shown in Figures 1, 2, and 3? Determine the pH range that corresponds to the steepest part of each titration curve and select an indicator or indicators that changes or change color within that range. The titration curve on the right is for the titration of a strong acid with a strong base. The steepest part of the curve spans a pH range of about 4 to 10. Most of the indicators in Table 17.3, with the exceptions of thymol blue, bromophenol blue, and methyl orange, would work for the titration of a strong acid with a strong base. The three indicators mentioned aren't suitable as the lower limits of the pH ranges, when their colors change, occur before pH of 4. Figure 2. The figure on the right shows the titration of a weak acid with a strong base. The steepest part of the curve spans a pH range of about 7 to 10. Cresol red and phenolphthalein are suitable indicators. Figure 3. The figure on the right shows the titration of a weak base with a strong acid. The steepest part of the curve spans a pH range of 7 to 3. Bromophenol blue, methyl orange, methyl red, and chlorophenol blue are all suitable indicators.